Hello, welcome to the second lecture of Deep Learning Theory and Data Science course. I want to talk about diffusion models. As I told you before, these slides are for Professor Vardan Papyan at U of T, Department of Mathematics. I have picked some interesting slides that I liked more, or something that I thought or of more importance, and I want to talk about these slides. Okay, today I want to talk about diffusion models. Let's see what happens. Okay, you can see the generative models are of very importance and popularity these days. Okay, as you can see, these are some images that are not real. These people do not exist in reality. These are some generated samples on celeb A, and these are some unconditioned CFR 10 examples. By unconditioned, I mean we didn't say what class you should create from these 10 classes. Okay. It's really interesting how these images were created from just an initial noise, and you can see that, for example, it is a church sample that we told the model to create this church for us, or create this bedroom for us, and it created these interesting pictures that do not exist in reality. Okay. I want to talk about first the graphical model of diffusion process. The diffusion starts from a noise, and step by step it adds something to the image, and then we reach this reach this image. Okay, it is the inference phase, but the training is in another direction. It means that we start from an image, and we should do some step-by-step actions, so we can go to this noise, and then we get back from this noise to this real picture, so we have to reconstruct it. Okay, when we are coming from this x of x in time, when we are going from this noise in time t, it is pure noise. Okay, when we are going from step t to t minus 1, it is the distribution p theta of x of t minus 1 condition of x of t. And when we want to go to more noise from t1 to t, it is the q of x of t condition of x in x of t minus 1. Okay, and you can see this diffusion process, we're diffusing some noise, and you can see, for example, here we are starting from a noise, less noise, less noise, less noise. You can see there is something appearing in these pictures. Some general idea of what is going to be is becoming more clear, and finally we are reaching this state. Okay. Another example that you see here, this is the conditioned one. We have conditioned it on some other pictures, and it's creating some images based on this conditioning. Okay, now I want to talk about the mathematics behind it. You know that when we are creating x of t from x of t minus 1, it is a normal distribution. Okay, we are just injecting some noise. What is the mean of it is you can ignore this sqrt. You can ignore this square root, and you can just consider x of t minus 1. Okay, it's some x of t would be something like x of t minus 1, but with some noise. Okay, And and also based on the Markov and chain rule, something like that, we can conclude that q of x1 to t conditioned on conditioned on x0 is is the multiplication of all of the q's, q of x of t condition of x of t minus 1 times x of t minus 1 conditioned on x of t minus 2, and so on. Okay, so we are adding those step by step. Okay, and we are transiting into a Gaussian distribution. Okay, now we want to talk about the reverse process. How can we go from x of t and x0 to xt minus 1? It is, again, it's not necessarily correct. We want this equation to be correct, and it's the place that we are placing our training process. We want it to be we want xt minus 1 in normal distribution from this and this. Okay, what is this? You can see that mu hat of t is something like this, and the beta hat of t is something like this. Okay, and so the reverse diffusion process becomes these equations, and we want to reverse the noise addition process, and we want to utilize learned parameters to approximate the denoising step. Okay, here we can see the cross entropy loss, which is this, and we replace, instead of p of theta of x0 with this integral, and then we replace then we added these two terms that if you multiply it is 1, but we're adding them. Okay, and then let's see what happens. We convert this integral to an expectation term, and then let's see what happens. Okay, you can see that we have expected of qx0, and here we have q x1 to t conditioned on x0, so we can delete x0 conditioning x0 here, and we can reach this term. Okay, but please note that it is an inequality. Okay, and then we can just let me see what happens here. Okay, we are removing this minus, so it becomes flipped and reversed, so it is the first term that we have here. Okay, now we have reached this this thing here, and we want to expand it more to see what happens. We expand it step by step with some simple actions. We first here we convert this q of x1 to t conditional on x0 to to a chain of multiplications. We convert the next one to chain of multiplications. We can extract some logs. The log of a over b would be log of a minus log of b. We use this we use this rule, and we then do the same things. We add some called terms here. Okay, we do some somehow direct things, and reach here that we have this expectation is not unnecessary. It's not correct to have an expectation, because the call divergence have this expectation inside it. Okay, So it is the call divergence between q of x of t conditioned on x0 and p theta of x of t, and the call divergence of q of xt minus 1 conditional on something, p theta of xt minus 1 and minus log of p of theta. Okay. I want to talk about the term decall of q and p theta. You know, all of these things are q and p theta. You have x of t and p theta of x of t that you can see here. Okay, which we call it LT. Okay, LT is this, LT minus 1 is this. It is LT minus 1. Okay, if we have two Gaussian distributions, the call divergence would be something like this, and we have from previous slides this one, and we can simplify this loss as this term, so we are predicting the noises, not the whole image. And you can see process of training and then inferring sampling. In the training we get x0 from the q0 distribution, and we get t from the uniform, epsilon from the normal Gaussian distribution, and then we take the gradient step on this one, which is the, let me show you, which is this one that we inferred here. And your sampling, we get x of t from just a normal Gaussian distribution, and we do for t steps, t is the steps for the diffusion process, and here z is from let me see. Oh, if you are in the first step, you know, I mean the last step, we can consider z to 0, and else we can consider z as normal, and we can do this equation. It is 1 over the square root of alpha t. Let me show you where is this term coming from. No, it is 1 minus alpha t over square root. You can see 1 minus alpha t here over the I have to find exact term we had in the first. I think it's originated from this one. We can convert it somehow to this. How can we get from? Okay, I think if in this distribution we put this expectation and these terms, we can get to this equation here. Yes. Okay, it's all the process of training and sampling of diffusion models that we can see. And just thank you for following. Like, comment, and subscribe, and email me if you have any questions. Thank you.